So what I was trying to say here is that this vector right here, this one is actually the orthogonal projection of this x. Okay, this one is actually if you put the torchlight from here, so you will see the shadow of this point all the way here. So this is called orthogonal projection of x. This is orthogonal projection of x on the direction of u2. So on u2, I would say, on the direction of vector u2. In the same way, this one is orthogonal projection of x onto u1. Okay, so we decompose that vector into two orthogonal vectors. What I'm saying is that this guy right here and this guy, these two are actually perpendicular. So if you don't trust me, then you just do the dot product. Okay, let us check that. So dot product is 6 and -9, dot 3 and 2. So what do you get? So this is 8. This will be 18 minus 18, which is 0. So this vector right here, this one and this one are perpendicular. So in another word, we decompose this x into two orthogonal vectors. This is called orthogonal decomposition. Okay. Now the question is, well, why do we need orthogonal decomposition? Does it have any applications in the real world? Let's look at that question now. So imagine you have your dog. Okay, I don't know how many of you have dog as a pet. Many of you, I think. Suppose this is your pet dog, okay, and you are going for a walk. So when you walk with your dog, then you are putting force in this direction. This is the force, okay? You are here. So you are here and you are pulling your dog. So what we want to do is we want to decompose this force into two perpendicular vectors, in two perpendicular force, like this. This one is the force, real force that you are applying to your dog. But if you can decompose this force into two orthogonal vectors, then it makes life calculation a lot easier. You will see, hundreds of examples in physics. If you have taken physics course, then there I think you decompose the force, the force into two orthogonal forces so that calculation will be easier. Okay, it has application in physics and engineering, and you can calculate by yourself just for fun, like how much force you are putting there. You can decompose that force into two perpendicular forces. Okay, now we already talked about orthogonal projection. Now let us look at this orthogonal projection again from a little bit different perspective. So as you can see, I have a vector y here. Okay, this is my y vector. And what I want to do is I want to decompose this vector. Well, I want to find the orthogonal projection of this vector onto the line L. So this is my line L. Okay, this is line L. And this vector here is U. This is the U direction. Now, if I use my torchlight to look at this, okay, torchlight, and you notice that the shadow of this point will be here. This is the shadow of this Y. And we denote that by Y hat. All right. We denote the shadow of this Y here on the line U by Y hat, meaning this one is perpendicular. Now notice that this direction is, this vector is U. So Y hat will be some scalar multiplication of U. It may be half of U, or it may be 2/3 of U. I don't know, depending on where you want to choose. So it is some scalar multiple of U. All right. Any question? Okay, now if this one is your U vector and this one is your Y vector, then this guy will be Y minus Y hat by using the triangle law or parallelogram law. So we can write this vector as Y minus Y hat. So what we have is, here is my Y, and this one is my U vector. And so I look at this from torchlight and I notice that, okay, torchlight, and then I notice that the shadow of this line will be here, which we denote by Y hat. Sorry guys, there was a, yeah, I was disconnected a little bit. So here, that's what this one, we denote that by Y hat. And this, see here, this one is your Y vector. This is your Y hat vector. And this one will be Y minus Y hat using the triangle law. So we can write this Y minus Y hat. Now, what we can say is that this is your lambda, I mean alpha U. Any questions so far? Okay, now one thing. This one is your orthogonal projection, means perpendicular. So what I can write is that Y minus Y hat, and then the dot product with U, U is this vector, must be 0. Does that make sense to everyone? Since Y minus Y hat and U are perpendicular, we can write that the dot product equals 0. So Y minus Y hat means lambda U dot U equal to 0. Okay, so that means Y dot U They all are vector, by the way. Even if I don't write the vector, then please understand that I'm talking about vector here. So y dot u minus alpha u dot u equal to 0. Okay, so can I write alpha u equals y dot u? Can I write that? So u. So alpha means is the weight, it's the constant. Okay, so the constant means in the earlier example in the theorem we wrote that as c1. C1 equals y dot u1 over u2 dot u1 dot u1. It's very similar to that. Just remember that this y hat equals lambda u, and lambda can be calculated this way. Okay, now too much talking. Let's apply this concept to solve one problem. Here is example 3. We are given y, we are given u. Find the orthogonal projection of y onto u and the complement of y orthogonal to u. Okay, let us, oh, by the way, this one is called complement.
Professor,
Yeah,
you're
yeah, sorry guys for the interruption, and I'm back again. In example 3, we are given a vector y and u, and we need to find the orthogonal projection of y, which means we need to find y hat. And component of y orthogonal to u, which means we need to find y minus y hat. This is called complement of y orthogonal to u. Okay. First thing first, let's work part A. So orthogonal projection. Orthogonal projection of y is given by y hat, and we already know the formula, right? Y hat is, the formula is y dot u over u dot u. Is that right? Because notice here that your y hat is alpha u, and we already calculated the value of alpha is this, so that means y dot u over u dot u, right? You just substitute the value. So this one, when you substitute, that's what you're gonna get. That is y hat. So try to memorize this formula, even though I will provide you the formula in the exam, but if you remember, that would be great. Okay, so this is the formula, and let us calculate that. So y is given, which is 7 and 6, dot u is given, which is 4 and 2, over 4 and 2 dot 4, 2, and then 4, 2. If you calculate the top part, 7 times 4 is 28, plus 12 is 40 on the top, divided by 4 times 4 is 16, plus 2 times 2 is 4, which is 20, 4 and 2, which gives me 2 times 4 and 2, or you can say 8 and 4. Part A is done. Any question? Oh, not done. We have to find the component as well. Orthogonal projection of y is given by this one. Now, component of y orthogonal to u. Component of y orthogonal to u is y minus y hat. So let us calculate this. Y is given 7 and 6 minus y hat is, we just calculated y hat, which is 8 and 4. So that's going to give me -1 and 2. That's it. Done. Now you can verify that in part B. Let's first work with part B, and then we talk about how to verify that our answer is correct. Okay. So in part B, we want to decompose y as the sum of two orthogonal vectors, one in a span of U and one in orthogonal to U. Notice that this y hat is actually a vector in U. Okay, y hat means it is a vector in the direction of U. And this y minus y hat is a vector perpendicular to U. Look at the graph here. Look at the picture as we have seen earlier. Y hat is a vector in the direction of U, but y minus y hat is a vector perpendicular to U. Okay, so basically what we want to do is in part B, decompose y as the sum of two orthogonal vectors, which means one is y hat plus another is y minus y hat. All we need to do is this. And y hat we already know, 8 and 4, plus y minus y hat we already know, which is -1 and 2. Okay, so they are perpendicular to each other. Does that make sense? Now, whether our answer is right or wrong, let us check that. Okay, just for fun. Let us check. So 8 and 4, 8, 4 plus -1 and 2, if I combine them, what do I get? I will get 7 and 6. Is this y? Are you sure? What is y given? 7 and 6, yes. You see, we decompose that 7 and 6 into two vectors. This one is 8 and 4 is in the direction of U, is in span of U. Okay, span of U means it is in the direction of U, and this one is perpendicular to this vector is -1 and 2 actually belongs to a span of U perp, perpendicular to a span of U. Okay, that's how we decompose the given vector into two orthogonal vectors. Any question? Okay, so another concept that we'll be talking about in this lesson is orthonormal set. Orthonormal. What does that mean? Here is the definition. A set, guys, listen very carefully for the next few minutes, okay? It's very simple if you understand, otherwise it will look really complicated, okay, if you don't pay attention. A set U sub 1 all the way up to U sub p is an orthonormal set. Orthonormal set if it is an orthogonal set of unit vectors. Let me repeat that. Orthonormal set means it is the orthogonal set of unit vectors. Okay, and if W is the subspace spanned by such a set, then U sub 1 all the way up to U sub P is an orthonormal basis for W. And one simplest example of orthonormal set is actually the standard basis that we discussed in our previous chapter. Now let's quickly look at this example 4, and I think you understand what we are talking about in that theorem. Okay, first of all, so that the B sub 1, B sub 2, B sub 3 is an orthonormal basis of R3. Okay, we need to show that this is an orthonormal basis. Do you want to try it by yourself? Here is a hint. We need to show two things. One is they are orthogonal. Okay, first you need to prove that they are orthogonal. So two condition. B1, B2, V3 is orthogonal set. Try to show that. And second, V1, V2, V3 are unit vector. So you want to show these two conditions here. Okay, guys? So I want you to find the dot product, B1, B2. So the dot product will be, this is 3 times negative 1 will be negative 3 over square root 66 plus 2 over square root 66 plus 1 over square root 66, which is 0. In the same way, you can calculate B1 dot V3, how much is that? V2 dot V3, how much is that? Okay, I'll leave it to you and let me know whether they all are the dot product, all of the dot product are 0 or not. Okay, all right, so guys, you already got the answer for all of these. I can see that in the chat box. Yeah, so this one is also 0, this one is also 0. So that means we can say that therefore set B1, V2, V3 is a orthogonal set. Any question so far? Now we need to show that the second condition, we need to show that V1, V2, V3 are unit vectors. Okay, to show unit vectors, we have couple of methods to do that. One is find the norm of V. Okay, you can do this by, let's say, method 1. Find the norm of V, which is norm of V1, which is 3 over square root 11 square plus 1 over okay, 1 over square root 11 square plus 1 over square root 11 square. So that's going to give me 9 over 11 plus 1 over 11 plus 1 over 11. Is it a unit vector? So you'll get 11 over 11 is square root. Yes, it is a unit vector. Okay, in the same way, you can try with V2 and let me know whether it is a unit vector or not. In the same way, try V3 and you can tell me whether it is 1 or not. I leave it to you. That's method 1. I see that you guys already checked, already verified that all of them are unit vectors. That's one method. And if you want to do this by another method, you can do this way too. So method 2 is, you can do v1 dot v1 equals, it should be 1. Okay, v2 dot v2 should be 1. v3 dot v3 should be 1. Let us check that. If this is 1, that's another way to check whether the vectors is a matrix, unit vector or not. So v1 is 3 over square root 11, 1 over square root 11, 1 over square root 11 dot 3 over square root 11. You know why? Because if v1 dot v1, so it's 1, if they are unit vector, 1 times 1 is 1, right? So we can use this idea. And so you're going to get, this will be 3 over 11 plus 1 over 11 plus 1 over 11, which is, this is 9 over 11, which is 11 over 11, which is 1. In the same way, you can calculate this will be 1 and this will be 1, okay? That's one method, and here is another method we have seen already. So all of them will be 1, no matter which method you use. You can show that these vectors are unit vectors. Therefore, since v1, v2, v3 is orthogonal set and v1, v2, v3 are unit vectors, it is an orthonormal set. Orthonormal set. Okay, so we know now that orthonormal involves two conditions. Okay, orthonormal means the set must be orthogonal and the vector must be orthogonal and the vector must be unit. Orthogonal unit vectors, when you combine them together, it is called orthonormal. Okay, orthogonal set of unit vectors is called orthonormal set. Any questions so far? And by the way, this process of finding the orthonormal set is called normalization. Okay, normalized. In this case, we call it normalization of the vector. The process of finding the orthonormal set is called orthonormalization. All right, so if you have any question, let me know. Otherwise, we are done with this section. So in our next section, we will look into this orthogonal projection in further details, okay?